Welcome, everyone. This is an introductory topic to something you may or may not have heard about, but I promise you that it is extremely valuable, both as something to know, but it could also help you land a job, especially if you're interested in working in a field where you design parts for manufacturing. So, a little bit about me before we get started. I'm a mechanical engineer in training with about 3 years of experience working in the automotive sector, and this is where I was initially introduced to GD&T as a topic. I went through formal training, and I was even given this nice little book as reference material. I wouldn't call myself an expert in GD&T yet, but I am familiar, and these sessions are aimed towards beginners of the subject. So as a bit of a heads up, this is being released for free on the internet, but it's also being designed for MUN students to participate in something called GD&T Club. We're doing our first pilot coming up in March, so if you're a MUN student interested in GD&T, or if you want to learn a topic that could help you land a job in manufacturing, keep an eye out for the announcement. So first, we need to know what GD&T is and why it matters. So the most obvious visible difference compared to traditional dimensional tolerancing, so your typical XY linear tolerances, are just how different drawings look like when using GD&T. This might seem intimidating, and to be fair, GD&T standards do have a fair bit of stuff to remember, but the basics are pretty simple, and that's what we're going to start with. For now, we don't have to worry about this drawing. So we know what it looks like on a drawing, but what is it? GD&T is short for geometric dimensioning and tolerancing. The name gives away what GD&T is about. It's about geometry more than it is anything else. It is an international engineering language that uses a standardized set of symbols to precisely define the geometry, the design intent, and the allowable variations of a part. The design intent is, in my opinion, the most notable or important thing to remember here. When you submit a drawing to be manufactured and you get something other than what you expected, it's usually because the design intent wasn't clear to the people who manufactured the part. GD&T is a symbolic language. There's absolutely no English or otherwise written language on the example drawing here. This is a purposeful feature of the GD&T symbolic language. International collaboration is a regular aspect of manufacturing, and this symbolic language aims to remove any interpretation error that may occur when using language. There are two competing standards for geometric dimensioning and tolerancing. The ISO GPS set of standards, which are primarily used in Europe, and ASME Y14.5, which is the standard primarily used in North America. So I'm in North America. My experience is entirely in North America. So I will be focusing on ASME Y14.5 and specifically the 2018 revision of the standard. So that begs the question, what is the issue with regular dimensional tolerances? Well, everything is basically just simple linear or angular measurements. That means that geometry is not very well toleranced. Let's use a admittedly silly example to demonstrate this point. Let's say we want a stainless steel cylinder with a nominal diameter of 33 millimeters. Maybe we're designing a metal rolling pin for baking, but we don't really care too much about what the actual diameter is. After all, what is plus or minus a couple millimeters for a rolling pin? This relaxing the tolerances here should help ensure that the manufacturing costs are reasonable. This is what we get. It's a cylinder. If we were to measure this with a caliper, it'll fall within the plus or minus 2 millimeters everywhere. So we've got ourselves an acceptable rolling pin, right? Well, obviously not. We could fix this by setting very tight tolerances, but then we might be paying hundreds of dollars for a rolling pin. And honestly, that's something that should cost an order of magnitude less. In this admittedly extreme example, the design intent wasn't clearly communicated. I think that the most important thing to remember is that GD&T controls first and foremost the geometry of a part, but not the scale or size. Although it does enable a new way to do dimensional tolerances, which we will see later. Here's a more realistic application of GD&T cylindricity. Let's say we have a bushing and a shaft. You may not be super concerned about the actual diameter of this shaft, because after all, it's supported by a wedge of lubrication. But but with so you can issue large tolerances, but again, with large linear tolerances, you can end up with an exaggerated example on the right. Obviously, it won't look that crazy, but this is just to prove a point. Even if you don't care that much about the diameter of this shaft, you should still be concerned about its cylindricity. Even if the shaft fits through the hole, if it isn't round, it will cause vibration, it will cause uneven wear, and it will destroy the oil film wedge needed for that lubrication. With geometric tolerancing, you could just control the cylindricity of a cylinder independently from the diameter's dimensional tolerance. That way, you can ensure that no matter the cylinder's diameter, you always have an acceptably round cylinder. But we're getting ahead of ourselves here. The main thing to know right now is that GD&T, and particularly ASME Y14.5, provides a symbolic language to control the form, the orientation, the location, the runout, and the profile of features on a drawing. You may recognize a few of these from CAD, especially when you're constraining a sketch. For example, you might make two lines parallel or perpendicular. These are similar. We will later explore what each one of these do. So, if it isn't obvious yet, why learn it? Aside from the fact that GD&T is useful, about 1/2 of the world's manufacturers use GD&T. It could very well help you land a job, especially if you plan to work in manufacturing. So my experience with automotive manufacturing, automotive uses it to manage complex assemblies in high volume production for many different and often international suppliers. Aerospace uses it for safety critical and high performance components where the factor of safety might be pretty low in order to save weight. The military uses it to ensure part interchangeability, especially when replacements need to be done in the field, where failure could mean life or death. Medical device manufacturing companies often use it as a part of a quality management system, which is a requirement for regulatory compliance. Lastly, companies producing consumer goods and industrial equipment use GD&T to reduce manufacturing costs, to reduce scrap rates, and to avoid inspection disputes by allowing for the widest possible tolerance range that still preserves functionality. And this is tailored towards engineers, but you might not think that GD&T is entirely an engineer's job to know, but perhaps more of a draftsperson's or a technician. But I see ASME Y14.5 on engineering job postings all the time. I saw one, for example, on a Kraken Robotics job posting, and a quick Google search reveals that GD&T is used pretty much anywhere that there is manufacturing done. Although to be honest, this list isn't fully complete. This list is a incomplete list of companies that use GD&T or that may use GD&T in Newfoundland. So here in Newfoundland, DMI, which is Design Manufacturing Inc., Kraken Robotics, and DF Barnes. So knowing how a part will be drafted with GD&T also means that you have an idea for how parts function in a mated assembly, as well as how they are manufactured and inspected. This goes a long way to ensure the manufacturability and the functionality of a part that you design. This is a big reason why employers usually like it when an engineer understands how to read and design parts using GD&T. So let's do a brief overview of why and when GD&T came to be in the first place. So it used to be that design and manufacturing was largely done just in-house. So back in the day, Ford Motor Company and Boeing basically didn't outsource anything. Everything generally was drafted, machined, and assembled in-house. And this is very different from today. These vertically integrated companies often relied a lot on the skills of individual machinists. They were often tasked with finishing parts to fit a specific assembly, adjusting dimensions manually through filing or scraping until components mated correctly. This meant that parts were not intended to be interchangeable. That is a big thing. Parts were not meant to be interchangeable. Drawings of this era relied on dimensional X-ride tolerances, which specified allowable variations, very much like today, but left its geometric relationships to other features implicit or undefined. Oh, and by the way, the drafting was done completely by hand, which certainly made creating drawings a lot more tedious of a job than it is today. And just as a note, these pictures were generated with AI. That's because a lot of the best images that I could use here are licensed. And considering I'm releasing this for free, I'm not going to license materials. So there are very real images that look very similar to these, and they were taken in the 1950s. So the origin of GD&T is credited to someone named Stanley Parker. And Stanley Parker was a machinist working at the Royal Torpedo Factory in Alexandria, Scotland. As far as I can tell, he was the first person to have applied geometric concepts to where there weren't any previously. His first and most notable contribution was with regard to waste. He found that parts were being unnecessarily rejected for quality reasons, even when they were perfectly usable. This is because traditional X-Y dimensional tolerancing creates tolerance bounds within a square or rectangle. But for tolerances such as ones that govern hole placement, the tolerance bounds that usually matter are circular. A hole center often needs to fall within a circular tolerance bound, but not a rectangular one. By restricting the tolerance to a square, the industry was needlessly rejecting parts that fell within the circumscribed circular zone. So here's a good example. This would be accepted here in this corner, if you can see my mouse, but here it wasn't. So, but this is essentially a further distance than this is here. So by changing it to a circular zone, it reflected the reality of the actual quality requirements for this part, dimensional requirements for this part, tolerance, I should say. Parker's ideas were formalized in a publication named Notes on Design and Inspection of Mass Production Engineering Work. These ideas eventually led to the U.S. Department of Defense releasing their own standard. In 1949, the US government created the MIL SCD-8 standard as a response to many logistical failures that the military experienced during World War II. Some of these failures were due to poor quality control, where parts would fail while being used on, let's say, the front line. Other issues were that parts weren't designed to be interchangeable, making equipment repairs in the field a lot more difficult. Eventually, in 1957, the Association of Mechanical Engineers, so ASME, published the Y14.5 standard. This became the new unified standard in North America for geometric dimensioning and tolerancing for much more than just military use. All right, so we know the backstory. Let's look at a really good example of a situation where GD&T is extremely useful. Let's say we want to create a brake rotor for a car. So you might whip up a drawing that looks something like this. So far, so good. This is what we might get at the end. Does this look like an acceptable brake caliper to you? I'm talking about this right here. You can see it's warped here at the edges. Some of the angles aren't straight back here. It's not a unified thickness. According to the drawings, it falls perfectly within the tolerances. You can see here the dimensions here. All these dimensions actually fall within the requested dimensions on the drawing. So let's take a set of calipers and measure these spots. Sure enough, it confirms that it's a perfectly acceptable part according to the tolerances we set. If we were to measure every spot in this warped example, you would see that it respects every tolerance indicated on the drawing. But if you've ever driven a car with warped rotors, you would know that this isn't acceptable for the application. This would vibrate like crazy, so much so that you could lose control of the vehicle. That's assuming you could even install it on the vehicle. This specific problem is caused by the fact that linear measurements are only local measurements. And by local, I mean like locally measure with a pair of calipers here, locally measure with a pair of calipers here, or micrometer. You really can't relate one feature to another. So how do we fix it? Well, maybe we want the brake rotor surface to be parallel to the mounting surface. Perhaps we want these surfaces here to be perpendicular. And lastly, perhaps we want the center of this cylindrical borehole, so this one here, to line up with the center of this cylindrical borehole. We can do all of that with GD&T and more. So here is a drawing tolerance using GD&T. You don't need to understand it at this stage, but I do want to point out a few symbols. Here we have the geometric tolerances controlling how parallel the surface, these surfaces here are to surface A. And this here controls how perpendicular this cylindrical borehole is to surface A. By the way, I mentioned earlier that understanding GD&T also means understanding how a part functions as part of a mated assembly. What were to happen if we had large tolerances on in the perpendicularity? Well, it may not even mate properly with the other parts, for one, but if it could, it would likely rotor. We have it on an angle and it rotates. Obviously, it's gonna wobble as it turns. And here we have the geometric tolerances controlling the position of this outer hole relative to the position of the inner hole with a center line datum B. So this is the center line datum. And the same thing here. What would happen if we allowed for large tolerances of the relative position between these two holes? Well, the same mating issues could apply, but it could also oscillate up and down. So, all right, that's enough for chapter 1. I hope that this served as an introduction to why GD&T is worth learning. And I hope this gives you a good intuition in the general topics of GD&T. We'll dive deeper into the topics in the next few chapters. So because I didn't make all this stuff up, I had to reference sources to learn all this. These are my sources. Thank you very much.